shock is hard. It's not always there. It depends on the environment and the system itself. But if we can detect it, it helps us to understand what the jet is made of. Is it baryonic, or is it Poynting flux or magnetically dominated? And we can also study the initial Lorentz factors as well associated with these relativistic outflows. And it's possible at early times, once again, we could see some kind of central engine, magnetar energy injection related emission as well. And this process that I've explained here, it applies to both long and short gamma ray bursts. So first I'm going to talk about short gamma ray bursts, because while the physics is the same, the evolution we observe is quite different for both objects. So there's a very strong motivation for us to study short gamma ray bursts in the radio because of that link with gravitational waves in 1708-17. But since we've been observing short gamma ray bursts, only 17 have been detected in the radio band. And I've got these plotted here, flux density or brightness as a function of time. They are the black dots and also the coloured ones in this plot. Of these 17, 11 were detected within a day post-burst, and then 8 of them have faded within a week. So these things are extremely bright, not extremely, they're bright initially, but they fade quickly. So we really need to be on target within 24 hours post-burst, but also be able to sample them very high, sample them well in time, but also we need it to be very sensitive. So I started as part of my DECRA triggering on short gamma ray bursts back in 2018, and we've triggered on about 7 of them. It wasn't until last year, way after my DECRA finished, that we finally got radio detections. So we had limits on 5 of them, and they are the white triangles in this image. But then in February last year, we had a detection of a short gamma ray burst, which are the magenta data points here. And so this data point, these 3 data points are actually from the same 7-hour observation that I've sliced in time, and this represents the earliest detection of any gamma ray burst to date. So I was on target in 32 minutes, observing for 7 hours. So this first, when we split it up, this first time bin is at 1 hour post-burst. And we can see that it's just decaying. When you split up an observation, you necessarily are reducing your sensitivity, which makes the error bars bigger. So it's very hard to see whether any of the modulation is actually real. This is actually a VLA data point. Back to ATCA again. I think there is something a bit wrong with the flux density scale from the VLA, which we sort of compensated for. But essentially it's declining, and this is a pretty classic reverse shock emission. So this is the 5th short gamma ray burst with a radio reverse shock emission, where the reverse shock is from the jet. And being so early in time, we actually have put the highest minimum Lorentz factor measurement on any short gamma ray burst to date of above 50. So this is very much demonstrating the power of being on target very, very rapidly to try to understand this radiation. And after our observation at 1 day, it then faded below detectability. So we really needed to be on target quickly. And then in November last year, we had another trigger, and this is from a very bright gamma ray burst that's also nearby. I think it might be the closest short gamma ray burst. It's definitely up there. And we were on target 1.3 hours post-burst, observing for 9 hours. I split this into 1 hour time bins, and you can see the 5.5 and 9 gigahertz observations. It's modulating a lot. That's actually from scintillation. You cannot get away from that in the radio band. But I've plotted in grey data points a check source in the field, which shows the variability we're seeing is real. And we're pulling this together with observations with other radio telescopes, including Amy, E-Merlin, and Meerkat. And one of the weird things about this is that with afterglows, we usually expect some kind of temporal evolution, rises, decays, but instead we've got quite flat emission. Here we've got this sort of flat light curve. And this can indicate some kind of energy injection is going on, or you could be having some sort of internal shell collisions, which are sort of essentially creating other synchrotron components that we're detecting. And so this was quite a weird signature, something that's never been seen before. And I'm now working with a big team, with the OnGrave team, with optical and X-ray data as well, for us to try to understand this event. A paper has already come out on this, and they produced this plot here. So this is the ATCA measurement we reported in a GCN before we cut it apart, and this is the VLA observation. So they only have 2 data points within that first day post-burst, and then it seemed to rapidly decay. They see what they detect is a forward shock that's been refreshed. So you have your expanding ejecta, creating the forward shock, expanding out into the medium, but then something else, a faster shock comes along and hits it. And that refreshes it and makes everything brighter again. But the radio is still brighter than we expect at early times. And they look at the idea of a reverse shock emission, or a reverse shock coming from that shell collision. Sorry, did you have a question?
Yeah, is it okay if I...
Absolutely.
What are all the other lines on that?
Good question. Those are all the other radio detected gamma ray bursts.
Over time?
Yes, as a function of time. Yeah, flux density over time. So it's sort of, this paper looks at the full population of the radio detected events as well. But yeah, the green stars being the key ones for this particular event. And I've then done the same thing, but put all the other gamma ray bursts in black to try to make it less confusing, maybe. So again, the pink is the one that we detected in February, and then the yellow crosses is this new one from November. And we can see just how much more powerful and brighter it was in the radio. But one of the key points I want to make here is that it's only with the rapid response mode that we're actually probing within 0.1 days post-burst. So we can actually study the afterglow in this early time, this regime that's never been explored before. And we've got a lot more information about this early time radio emission, which we're including in our modelling as well. So this is the modelling that we've been doing. This is being done. I didn't put his name on here. This is Gavin Lamb. He's sort of one of the big gamma ray burst model people. And so we have X-rays down to optical down to low frequency radio. And he also finds that after about a day post-burst, we've got this forward shock that's been refreshed by a shell hitting another one. But again, it's not predicting these low frequency radio emission. And this is a very common theme in gamma ray burst astronomy. Everything works until we get to the early time radio. And so he's now incorporating in some kind of reverse shock from this violent collision that's occurring at the moment to see if it can actually approximate what we're observing, bearing in mind we also have scintillation, which makes things quite tricky too. So this is a work in process. We're in a bit of a holding pattern at the moment, but we're slowly unpicking what's going on and trying to understand it. Okay, so just to finish up, I also wanted to talk about my long gamma ray burst observing program, which I've called PanRadioGRB. So it's once again utilising the rapid response mode of ATCA and then doing multi-frequency high cadence follow-up. And we're trying to do this of all of the gamma ray bursts detectable in the Southern Hemisphere. So up until this point, with radio telescopes being, but there being far fewer radio telescopes than, say, optical and other instruments, usually gamma ray bursts are only chosen for follow-up if we know something special about them, like they're nearby or they're optically bright. So we're just saying, no, we're going to do an unbiased survey of all the ones detected with Swift. And we've got over 1,000 hours of telescope time in the last couple of years in order to try to do this. And so we followed up 17 gamma ray bursts to date. We've got about 5 detections at the moment, which is actually less than expected. And once again, because this is unbiased, and before now it's only the optically bright ones that we observe. But the general idea for the science goals of this very sort of complete survey is to understand the source of early time radio emission, the composition of the GRB jet, the geometry of the outflows, whether or not there is a universality to blast wave physics, to the physics of these outflows that we're observing, the total energy budgets in gamma ray bursts, and the density profiles of their surrounding environments. So these are sort of the key science goals that we're looking at. And this was motivated by a gamma ray burst we accidentally triggered on in 2021. We thought it was a HESS detected one, but it wasn't. But we actually observed this radio flare. We were on target at 5 hours, and then it flared at 9 hours. And it was the rise in decay was far faster than we expect from any kind of afterglow, forward or reverse shock behavior, and it had a positive spectral index. And we think this is interstellar scintillation again. We can actually use it to place a source size on the radio emitting region, and this is the earliest source size that we have to date for a gamma ray burst, which is consistent with models. But whether or not, but another team has the multi-wavelength data, and so we don't know whether the radio afterglow was bright enough that scintillation could have boosted it to the point of being detectable on minute timescales with ATCA. So this is an example of this unexpected radio emission that we're now seeing that we can't explain very well at the moment. Yes?
Could you elaborate on how the interstellar scintillation causes a brightening?
It's sort of like a magnification, essentially, from the material that's actually in our own galaxy. You have some kind of what we call a scattering screen, and that essentially amplifies and then causes or magnifies it, or causes it to also get dimmer as well. And you just can't get away with that at low radio frequencies. But it only happens when the radio source is a point source. As the afterglow expands, or as the jets essentially plow further away, it becomes bigger than what we call a scattering scale, at which point it stops scintillating because it's too big for it to be magnified, in a sense. And that's how we can get a source size measurement. I'm just going to go through this quickly, but we've been monitoring two gamma ray bursts for quite a long time, this one for nearly a year. No rapid response observation, but it appears to be just a normal run-of-the-mill radio reverse shock with a possible jet break at 40 days. And then we have this one as well, where we actually have a rapid response detection at 14 minutes. So I suppose technically this one is an earlier detection, but I haven't yet had a chance to properly explore what's happening at those early times. But it's interesting that we can track these to quite late times, particularly to lower frequencies. So this is where we got simultaneous observations with Meerkat and ATCA, and we can really start to constrain what's happening at the very lowest radio frequencies, how gamma ray bursts evolve. When basically, particularly with the one on the left, we've been observing it for nearly a year. Only about 3 long gamma ray bursts have been detected out to, there could be a few more, out over a year. And that's where we can really understand what's happening at the shockwave physics when the blast waves slow down to non-relativistic speeds. Finally, I just wanted to give a bit of a shout out to the boat. This was coined the boat because it's the brightest of all time. It was a gamma ray burst on the 9th of October 2022, and considered a 1 in 10,000 year event because it was extremely gamma ray bright and very nearby. But this 1 in 10,000 years, I'd have to say it's probably an over-exaggeration since we've been detecting gamma ray bursts at 50 years. But still, it was pretty amazing. And Amy was on target in the radio band at 3 hours, and we saw this beautiful reverse shock with this amazing spectral coverage. Never seen anything like this before. About 25 times brighter than the radio reverse shock emission. And so because of how bright it is, we could really observe it and sample it with high cadence at multiple frequencies. And what's interesting is we could actually see 3 bumps. So we've got the first bump, the reverse shock, second bump, which is from the forward shock, but there's actually a third bump. So these, particularly these observations down here, are also taken as part of the PanRadioGRB program. And it's possible the third bump could be a wider outflow. So do we have a structured jet? Do we have a jet embedded in a cocoon? And so these are the things that we can really study if we have long-term radio monitoring and if the gamma ray burst is bright. But we also know that it's expanding into a wind-like medium, and we haven't detected a jet break. So the jet is basically continued to be relativistic, it hasn't slowed down. And in order for that to be the case, for nearly 500 days post-burst means it would have been really high kinetic energy in that jet. Okay, so that brings me to the end of my talk. I've talked about the motivation for low-frequency radio triggering using the Murchison Widefield Array to try to search for FRB-like signals. We've got a lot of limits on short and long gamma ray bursts, and we have a observing strategy for O4. And with the higher radio frequency triggering with the Australia Telescope Compact Array, we've been focusing on short gamma ray bursts for a while, and we finally have 2 detections, some of the earliest known radio detections of gamma ray bursts, one being a reverse shock and the other being some kind of energy injection or violent shell collision. And we've also begun PanRadioGRB with 5 detections so far, and we've been doing long-term monitoring of 2 gamma ray bursts. So the rapid response observing systems are revealing exciting science. So let's see what we can do with SKA. Thank you.
I was wondering if way back towards the start when we had the table up about the probabilities of seeing FRB-like emission.
Yes.
I was wondering if you could talk a bit more about what went into calculating those.
Sure. Okay. This table, it actually looked at, in this case, it was actually 6 different configurations that we could put the MWA in, such as using just a full array with a single beam, a single dipole to look at more of the sky, or splitting it into the subarrays and which one of the subarrays would work best. It assumes that we continue to point at the same region of the sky even if positional information becomes available. We do repoint, but it's assuming that it doesn't. What is the probability that if something winds up in that region and that we somehow continue to observe that region, that we could detect these signals? So it takes each of these models and it took a population of binary neutron star mergers with different inclinations, and we attenuated all of these emission models with the inclination of those binary neutron star mergers to see how the viewing angles change. And for a lot of them, we can't really see much past about a 30-degree inclination, but with these last 2 ones, it wasn't so much inclination as sort of the assumption on how widely the emission is beamed. But we can talk more about that later if you like. And then we took that population and said, okay, what's the probability of it being in this part of the gravitational wave sky? And then we convolved it by the response of the MWA beams as well. So it was essentially these 3 different parts to it. Does that help answer your question?
Yeah, but I might need to ask you more.
Yeah, sure.
As well. Thank you.
Yeah.
Thank you for a very interesting talk, Gemma. So it's perhaps not surprising that as we get more and more data and better data, we find that nice simple models for what the afterglow might look like in terms of its time evolution, in some sense, no longer work, right? And you see more features, and the question is, of course, where those features are coming from, right? And so you and some of the previous authors in this try to explain this by more complicated physics within the interaction, right? So things like refreshment, forward shocks, reverse shocks, etc. But just to throw out there at least 2 more possibilities, right? And I'm not advocating for them, just saying that one could consider 2 more things, right? So one is that the jet structure itself could be more complicated than in principle, at least in the sort of typical models people assume, right? So top hat, it's very simple model. Okay, then people move to more complex models like, say, okay, maybe it's a Gaussian profile or something like that, right? But it could be something even more complicated, right? It could be that you have some sort of a corkscrew, for example, right? Because you could have imagined that the source is precessing while it's emitting a jet, and so you have some much more complicated things here. People have talked about these kind of open cones, okay, still retaining the axis symmetry, but having instead of having a peak at the center like a Gaussian profile, with having I think Jonathan Greneau, for example, had this model at some point, right, where you have more like a like the thing on a lamp, right, that sort of looks like this, right? So anyway, just a possibility that it could be something like that, and of course we can make it arbitrarily complicated to fit the data. I'm not suggesting that that's useful, just saying that it's kind of worth considering. And then the other question I had was, could it also be something about the structure of the ISM itself, right? So the typical models, I think, assume a homogeneous interstellar medium, right? But again, do we know whether the ISM necessarily has to be homogeneous, especially if we're looking at relatively early times where perhaps we're still interacting with some of the ISM that's polluted by previous ejecta, let's say, from the same system? Could it be that there's some local homogeneities that are causing these interesting behaviors?
Yep. So for your first comment, when we first saw this, we actually did think about this idea of that corkscrew, and that maybe we were seeing the edge of a jet, of a relativistic jet, which could cause that. We also were thinking about like if there a thermal population of electrons, so not all the electrons were accelerated into a power law distribution, that some of them are just radiating thermally, which you predict have radio emission at early times. But at least in this case, what we do try to do is stick with the simplest explanation we can. So unfortunately, I really wanted it to be something cool like that, but the somewhat limited models we have of the interstellar medium said that it could be scintillating up to a certain modulation index. That's what we observed. So its simplest explanation is interstellar scintillation. In terms of this one here, you could have a flat spectrum, a flat light curve from a forward shock in a wind-like environment. Yeah, that is true. I think at the end of the day, we are just limited by data, and we have to make assumptions. And it's unlikely. So originally we didn't know how much the fact that this refreshed forward shock seems to work with most of the data was like, okay, let's not complicate things. But now we really have demonstrated, all right, we do have this additional component. Yeah, I understand what you're saying. But the fact that would mean that there would need to be 2 forward shocks in this particular case, which I'm saying is not impossible either. Too. So, isn't a refresh shock kind of a forward shock? 2 forward shocks as well. Yeah. For this gamma ray burst, of which we have few data points, even though we split them up as much as we could, this rapid decline is what we'd expect from a reverse shock in a homogeneous environment, but it's also the decline we expect from a jet break. But we have to say, okay, well, jet break's probably not going to happen that early in the event, otherwise it would have to be quite a narrow opening angle, and it could be from a flat light curve again in a wind-like environment. So, and again, we have to kind of go, well, early time, it's probably not a wind-like environment because it's a short gamma ray burst. So yes, I hear what you're saying, I completely agree, and you have to mention all these potential things, but we're limited by the data.
So can I then ask, what does SKA, and I guess in particular SKA bring in terms of on-source time and things along those lines.
More sensitivity.
Sure.
I think one of the things we're limited with ATCA is that it's an east-west array. SKA is going to have really good instantaneous UV coverage. MWA has that too. So the fact that we could do this was the fact it was bright and we could fit this in the UV plane rather than make images. We actually fit the visibilities for a point source every hour. But that's only doable with something bright. With the SKA, which will have hopefully a good UV coverage, we can probably also image on those shorter timescales as well. We've got better instantaneous sampling of the sky. MWA is great because you can actually create half-second images. And so with SKA low, more sensitivity. Yeah, but I think as I was saying yesterday, a lot of these models where a lot of these cases where we might have detected something, we're always scraping around in the noise. And every time we get a more sensitive telescope, again, we're scraping around in the noise. So I think until we get something that's actually really quite quite significant, and really it's only with more sensitivity.